So in sorting algorithm, today we will see quicksort, merge sort and quicksort. They are classic examples of divide and conquer. So merge sort, what it does, it divides the array or the values with respect to the middle position. Means it divides exactly the array or the values in half and then combine the step. So actually the combining step where all work happens, while in quicksort, which is somewhat different in terms of merge sort in this aspect, is that it does all its hard work in dividing the values or dividing the array, then calling recursively itself, and then combining. While the combining step is going on, most of the work is already done by division. What exactly quicksort does is that in an array or a list of values, for a pivot value, for any value which has been chosen, the numbers to the left side of this pivot value, these should be less than this pivot value, and all the values which are on the right side needs to be they need to be greater than the value. And I'm not saying that these two values which are less than or greater than, they are sorted by themselves. They may not be sorted, but these members should always be less than this pivotal value or the value which has been chosen as the center value, or these values on the right side should be greater than this pivot value. So we call them as this particular value, this position as a pivot element P. So we have seen that this is the basic idea of our quicksort. We recursively, or entire array is recursively sorted in this manner. Left side lesser number, right side greater number. But you will think that, okay, if I choose the pivotal or this P as the center, and you are thinking very correctly that this particular quicksort will come down to merge sort only if the pivot is central value. So this is how the algorithm is going to look. What we do in quicksort, this is an array, this is left, this is right, and if left is less than right, because the only condition is that left should be less than right, we partition, and this is the actual work which is shown here. We partition the array with respect to left and right positions, and then we quicksort. What we quicksort from left to m-1 and then m+1 to r, means this is the array and this is left, this is r, this is m, say any pivotal value. So we quicksort, this is for these values and this is for these values, and then partitioning, again calling quicksort twice for this quicksort. So recursively calling it. Partitioning is just checking a value and just seeing that all the values should be less than, and if they are not, we are swapping it. So a lot of swapping is going on. This is how the center point works, but how we see that the value we have just chosen is quite good. It means everything depends on the pivotal value which we have chosen. What is the pivotal value? And this partitioning, let us see a lemma that will actually prove this quicksort. When we are partitioning this A, L and R, this partition function, it returns the value M, which is the M value, pivotal value. The array A still contains the similar element. It has to contain the similar element, but with certain property that this value, each position L, should satisfy that AM should be either this should be greater than or equal to AI, or AI should be less than or equal to AM, and those values which are on the right position, these should be this central value, these values should be greater than the central value or the pivotal value. And this is a pictorial representation of the state of quicksort after we call the partitioning. And to prove this lemma, we would we have to go to the induction. Since partition consists mostly of a loop, we would need a loop invariancy also, which capture formally the outline of how partition works. And once we prove this, we can really say that Quicksort has been realized. And it simply uses strong induction on the array size, and this applies this lemma on the induction hypothesis. So we are not going to cover that right now, because this is doing things which are beyond the scope of this discussion, because we are actually interested in running time that we will do. So to analyze the running time of Quicksort, we use the similar approach as we did with merge sort, because both are recursive algorithm. We say that this Tn, this represents the worst case running time of Quicksort algorithm for any size n, and we'll see the algorithm line by line. So the call to this partition takes order of n. This one takes order of n, but it runs on a linear scan through the array, so we have some constant time also. Then we have to recursive call Quicksort for one partition to the other partition. So this is the first line, order of n. The first partition say tk, and then means we are calling it as k. So this partition, this was the first partition time taken. This is the second partition time taken, and t1 will be equal to theta n for bottoming up or coming out of the recurrence. And you see that this particular expression is actually going to be varying between n log n and n square. How? We have two conditions. You may take k equal to n by 2, and k n by 2, that means you are actually working as you did in your merge sort. So it will be only tn by 2, and theta n 2, tn by 2, and this that this is already we have proven in our merge sort discussion that this is order of n log n. While if we start from 0, or we take pivot value as, if this is an array, we take pivot value either this or this one. If any of this is taken, this will become as theta n t0 or tn minus n or otherwise. So the recurrence relationship will become theta n plus tn minus 1, and we know that what is tn. This is actually tn minus 1 or tn. This is theta n till theta 1, and this is nothing but sigma of theta I, that is theta n square. So ultimately this is becoming theta n square only. So this is very important what you choose. If you choose pivot value like this, then it will become order of n square. If you choose the middle value, this is order of n log n. Then what is the discussion? You are already thinking right now that okay, merge sort is better, but we have to choose a pivot point accordingly, and we have to choose pivot points such that we remain in between n square and n log n, or rather achieve better than n log n. So pivot value can be taken somewhat 25% value, means at certain point here, either this n by 4 or 3n by 4. So there is no concrete way how to decide it. There are ways, means you can use this swapping. You can have some random values. You can swap values in a quick sort, and so that it should be you can randomize and mix them so well. So these are the codes you can use, but always it is not possible that you go to some 25%, means the 1/4 position or 3/4 position, and then as a pivot value you choose that particular index and then start the work. So hopefully you got the idea that Quicksort and this merge sort, they follow divide and conquer, and Quicksort variates, as I indicated, that varies between n square and n log n. So pivot value is very important as far as Quicksort is concerned. So thank you so much. Take care.